Miss Stonebridge, tell us what you're doing.
All right, so I've got a bucket. It's got water in it, as you can see. We're going to swing this bucket, and we'll see what happens. Here we go. Is it too much water?
No.
That's just the base of shoulder. All right.
Was it close? What would happen if we added more water?
Let's see. And her shoulder, take it. It's heavy.
Are you sure you can do that?
Oh, yeah.
Need more. I'm worried about your shoulder.
Ooh, it slows down a bit.
Yay! All right, so due to the inertia, the water is staying in the bucket, and or the back of the bucket is keeping the water in. Just like you guys in a car, as you go around a corner, your seatbelt keeps you in your seat. The bottom of the bucket is keeping the water in the bucket, where if it weren't there, the water would go flying out.
Moral of the story, where's it?
Yay!
This bucket is full of water. The water is alarmingly not spilling anywhere because the inertia is keeping the water pressed against the bottom of the bucket even while it is at the top of its arc. It's also the first episode of our two-part mini exercise series, Buckets of Water, The New Kettlebells and You. Mr. Madsen has set up a ladder over here with the help of Miss Kramer. I wonder what they're going to do with it. We got to get in place for a closer look.
In a free fall problem, does the mass of the object impact how fast it goes when dropped from a height? So, I have a piece of paper and I have a microbiology textbook. Which one's going to hit the ground first? But when you take away the air resistance on the paper and you drop them from the same height, they fall at exactly the same time.
There we go.
Finally.
We're doing? All right, guys. We're heating up the can. It's got some water in it. We are going to see what happens when we immerse the can into some cold ice water in a few minutes here, or a few seconds. Need to let it steam a little bit. Ready, Freddies? It is boiling, steaming. Oh, spectacular!
So sick!
As you can see, it's been crushed.
Wow. That was some B- cinematography. What a can crush.
A+ physics.
Which one of these buttons is the manual focus? I'm learning how to focus a camera.
Bradley's in this.
Changing the focal distance and changing what the camera is focused on. I don't know how to use a camera.
What we need?
Tell us what we need.
Polarization. Polarized lenses.
Sound is also a product of physics. Sound waves are basically air particles being pushed together and then spreading apart. And then those little differential little moments in air pressure colliding with your eardrum are what makes sound. You can actually see waves on something like a stringed instrument where you actually see what is resonating to create those sound waves. So if I pluck a string, it makes a sound. It sounds a little bit weird because we have taped over the resonating chamber of this guitar. But if we look at the string, so when we pluck a string, hear a sound, and the string itself starts to shake. The sound that it makes, the pitch of the sound, corresponds with how fast the string is shaking. So if I pluck the string, it makes a particular sound. If I pluck the string and then I immediately change the tuning of the string, it's going to sound different and vibrate at a different frequency. Now when it's vibrating like that, you'll see it shaking differently. You won't actually see how many times it's vibrating because it's limited by the shutter speed of the camera. So what you're actually seeing is the camera interacting with the frequency of the string as it vibrates. When you hit a guitar string, When you have a finger pressed on the fretboard, you're actually seeing a compound waveform, which is a combination of many frequencies with a particular frequency coming out as the most prominent. But if you play a harmonic, which cuts out all of those other frequencies, you can see a perfect waveform.
He comes up here when he comes in, does he? This bag is for Keith and this bag is for Mark.
Mr. Chapin, what are you doing? Explain yourself.
This is a tuning fork. When you strike a tuning fork, it'll play a particular frequency. It plays a note. That note, well, it's an A. It vibrates at 426.7 hertz. That's the only pitch that this plays. You can hit it as much as you want on different surfaces with different objects. It'll always play that same frequency. But we can make it sound like it's playing a different frequency by moving it forward or away from our reference point. This is called the Doppler effect. If you've ever been passed by an ambulance on the highway, you'll notice that the pitch of the ambulance changes when it passes you. We can emulate that here by striking this tuning fork and spinning it around. The pitch it played never actually changed, but at the bottom of the swing, as it was moving towards the microphone, it actually compressed the sound waves as they were moving towards the camera. At the top of its arc, while it was moving away from the camera, it elongated the waves, making the pitch lower.
We have a rather ambivalent attitude to science at present.
We have come to expect the steady increase in the standard of living that science and technology have brought.
But people distrust science because they don't understand it or feel they can control it.
The popularity of science fiction like Star Trek is because it is a form of science with which people feel safe.
But an understanding of science fact would lay their fears to rest much better.
What can be done to harness this fascination with science and give people the background they need to make informed decisions?
On subjects like the greenhouse effect, nuclear weapons, or genetic engineering, the basis must be what is taught in schools.
But school science is often presented in a dry and uninteresting manner.
When he wrote A Brief History in Time, he was advised that each equation he included would halve the sales.
He included one, E equals mc squared.
Perhaps he would have sold twice as many copies without it.
Scientists and engineers tend to express their ideas by equations because they need to know the precise value of quantities.
But for most people, a qualitative rather than a quantitative understanding is sufficient.
This can be conveyed by words and diagrams without the need for complicated equations.
School science can provide a basic framework, but the rate of progress is now so rapid that there are always new developments that have occurred since one has had school or university.
Popular science books and articles can help to put across these new developments.
But only a small proportion of the population reads even the most successful book.
Television is one way to reach a truly mass audience.
But television is communication one way only.
Now with the internet, people can answer back and interact. In a way, the internet connects us all together.
Like the neurons in a giant brain, with such an IQ, what won't we be capable of?
So, remember to look up at the stars and not down at your feet.
Try to make sense of what you see and wonder about what makes the universe exist.
Be curious.
And however difficult life may seem, there is always something you can do and succeed at.
It matters that you don't just give up.